Welcome to our civil engineering project for Group 9. Our mission was to create something thrilling, which turned out to be a roller coaster. Here's the catch: we had limited time and resources at our disposal. We had to get as many points as possible, whilst ensuring the structure was safe and well designed. Here's the team we had on board. Shown on the briefing, 2 points are awarded for each second the ball rolls on the track. The jackpot was 100 points for a successful vertical loop, which we considered implementing, but the risks were too high. We used equations of the ball's motion for centripetal force. For example, at the top, mv squared over r would be equal to the reaction force plus the weight, and at the bottom of the loop, mv squared over r would be equal to the reaction force minus the weight. The risk is high, as the ball would have to reach a certain velocity, and it would have to start from a high height, as gravitational potential energy would be converted to kinetic energy, but this would risk the structure collapsing, as high momentum would mean larger forces acting. In our spare time, we decided to meet up in the engineering common room, as well as the engineering build space, to discuss the different design ideas that we thought up, as well as calculations, which led to the following innovations. Kiki's design was competitive for earning points, since it involves a vertical 360-degree loop. It also has a sharp 180-degree turn, which would award 15 points, and the barrier is also illustrated to prevent the ball falling off the track. The shelter at the end prevents the ball from falling, which avoids a harsh point deduction, and brackets ensure the track remains stable by accounting for forces acting on the wire. Design 1, shown on our group report, demonstrates a central support and analyzes the fact that the main structure cannot be circular, as this will be difficult to shape the material into. It therefore offers alternatives such as a triangular and square base instead. Large height was desired to get more points, as more loops can be implemented. This model also highlighted the fact that we had access to unlimited pins to strengthen the trusses. The aim of Design 2 is to get as many 360-degree turns as possible, with the diameter decreasing as it goes down. It has triangular base supports, but the model is not plausible because the smaller diameter track is not supported by anything, and the ball speeds up, meaning it is likely to fall off the track with a sharper curvature. This is the drawing for a quadrilateral support that inspired the bilateral design, which is also mentioned on the report. The intention of this was to use 180-degree loops with a small amount of manufacturing. However, there was minimal support for the track, so it was converted to a bilateral design by which the supports were moved closer together. Unfortunately, a significant amount of material would be wasted, which removes any room for support of the internal track. This is Design 4, the tower support model, which we ended up choosing by weighing up the pros and cons of each model, and by employing a Pew matrix, which shows that Design 4 had the higher score. This model is an adaptation of Design 3 that uses truss structures for stability while saving material. I'll now switch over to Tinashe, who will explain the design which he modeled using computer-aided design.
So here we have a scale model of the roller coaster prototype in CAD. The design is simple but effective. It uses 6 different truss support structures at these specific locations, 4 external supports which house the external portion of the track, and 2 internal supports which house the internal portion of the track. The supports use overhanging cantilever beams located at each level where the track is laid. The track itself is formed from a metal wire into 5 different layers on each side. It has 10 180-degree loops with 5 on each side and 1 90-degree loop at the end of the track. This completes the final design modeled in Autodesk Fusion 360.
For the truss structures on the supports, we found that the Warren truss pattern was the best design, as it spreads the load fairly evenly between members and is a simple structure. The angle between the members was decided through considering what would bring the best balance between structural stability and using the minimum amount of materials, and we came to an angle of 42 degrees between members. In this design, we used the method of joints to calculate the force for each member, and found that the side supporting the load was in compression, with the other side being in tension, and the diagonal line between joints altering between tension and compression to keep the structure together. The force is found to be more concentrated towards the bottom of the structure, with the highest force being 28.7 newtons. Fortunately, this is significantly lower than the critical vertical load of the balsa wood of 27 kilonewtons, therefore ruling out the possibility of buckling when supporting both the mass of the ball and the track.
Cavin's calculations involved finding the length of the wire and the arc of the turns by using circle geometry. He also found that we would be able to implement an extra 90-degree turn towards the end with the spare wire, and used Suva equations to determine the speed of the ball on the track. process of shaping the track was difficult as the wire was very tough, so we 3D printed a mold to help create the circular path. This is the final product, which helped us get a single run record of 186 points.
3, 2, 1, stop. Really good, really good.